The orchestra needs a conductor. Why the CPU is reclaiming the spotlight in the Agentic AI era. Presented by Chong Ho Alex Yu. Hello? In the era of AI and big data, no doubt GPUs, TPUs, and other powerful processors have been taking the spotlight on stage. Armed with thousands of miniature cores capable of performing mathematical acrobatics simultaneously, these specialized accelerator chips have been hailed as the undisputed engines of the machine learning revolution. They are the drag racers of the computing world, built for blinding straight-line speed when chewing through the massive matrix multiplications required to train deep neural networks. Nonetheless, it is still premature to completely rule out the importance of central processing units, CPUs, in the AI race. Far from becoming obsolete relics of the pre-AI world, the humble CPU is experiencing a massive corporate renaissance, establishing itself as the irreplaceable anchor of next-generation artificial intelligence infrastructure. To understand why this shift is happening, one must look at how the AI landscape itself is changing. The initial phase of the AI boom was defined by model training. Imagine this as a grueling multi-month academic boot camp, where a raw AI system reads the entire internet to learn how to speak. This process requires brute force computational power, a job perfectly suited for graphics processing units, GPUs. However, the industry is rapidly transitioning from building models to deploying them, entering the era of AI inference and, more importantly, agentic AI. Inference is simply the act of using a trained model to answer a question, like when you ask a chatbot to write a poem. Agentic AI takes this a massive step further. Instead of just answering a prompt, an AI agent acts as an autonomous digital worker. It can plan multi-step workflows, search the web, retrieve internal documents, write and test its own computer code, and call external software tools to achieve a complex goal. This evolution completely alters the hardware equation. While a GPU is spectacular at generating raw intelligence tokens, it is historically terrible at managing the logical flow of a complex business process. An AI agent does not just perform parallel math. It executes sequential logic, classic if, this, then that decision tree thinking. If a system needs to look up a customer's billing history, pause to verify an account status, branch into a separate data stream, and then execute a secure transaction, it requires a processor optimized for serial processing, rapid task switching, and flexible logic control. This is the exact domain where the CPU reigns supreme. Consider the metaphor of a world-class restaurant kitchen. The GPUs are the hyper-specialized prep cooks. They stand at their stations with razor-sharp knives, chopping vegetables at a dizzying parallel speed that no single person could match. But a kitchen full of prep cooks without leadership is absolute chaos. Someone has to read the incoming customer orders, manage the inventory, assign tasks to the right stations, ensure the food goes out in the correct sequence, and handle unexpected logic problems, like a food allergy or a broken oven. The CPU is the executive chef standing at the pass. It orchestrates the entire kitchen, ensuring that the expensive prep cooks, the GPUs, never sit idle waiting for ingredients to arrive. Without a powerful CPU acting as this system conductor, data centers suffer from a phenomenon known as GPU stalling. Because GPUs are built for massive throughput rather than complex data management, they must wait for data to be pre-processed, cleaned, and properly formatted before they can execute their math calculations. If the data center's CPU is underpowered, the ultra-expensive power-hungry GPUs will stall, sitting completely idle while waiting for the bottlenecked CPU to feed them data. In the economics of modern data centers, where a single AI server rack can cost hundreds of thousands of dollars and draw unprecedented amounts of electricity, letting a GPU sit idle is an operational sin. This reality has triggered a dramatic narrowing of what hardware engineers call the attach rate, the physical ratio of CPUs to GPUs inside an AI server. According to statements from Intel and AMD executives, during the early training-heavy days of the AI boom, a typical server configuration featured a lopsided ratio of 1 CPU to every 8 GPUs. Because the workload was almost entirely raw math, a single CPU coordinator was enough to feed a small army of accelerators. However, as agentic AI and complex inference workloads take over data centers, that ratio has rapidly tightened to 1 to 4, with market executives and research firms projecting it to narrow further to 1 to 2, or even a balanced 1-to-1 ratio. The explosive demand of data centers has turned the CPU market into a fiercely contested battleground, drawing in an array of aggressive new challengers alongside legacy giants. Historically, the CPU landscape was a comfortable duopoly, ruled by Intel and AMD using the traditional x86 hardware architecture. Today, the competitive field is wide open. NVIDIA, the reigning king of AI graphics chips, has aggressively moved into the standalone processor space with its new Vera CPU architecture. Mobile silicon pioneers like Qualcomm and MediaTek are scaling up their smartphone expertise to build high-performance processors for AI laptops and data centers. While cloud computing titans like Google, Amazon, and Microsoft are actively designing custom, proprietary CPUs tailored to run their internal cloud platforms. This influx of new chip design has also accelerated a profound architectural shift within the silicon itself. The traditional x86 architecture used by Intel and AMD is incredibly powerful and excels at executing highly complex, heavy computational tasks. However, it is structurally power-hungry. On the other side stands the ARM architecture, a design philosophy that grew up powering smartphones and mobile devices where every milliwatt of battery life matters. ARM chips achieve extreme energy efficiency by using a simplified instruction set, allowing them to perform tasks using a fraction of the electricity required by traditional processors. In the AI era, power has become the ultimate structural constraint. A modern AI data center consumes an astronomical amount of electricity. Industry estimates suggest that global data center energy consumption could soon rival the power demands of medium-sized industrialized nations. Because massive GPU clusters already run white-hot and draw unprecedented amounts of power from local electrical grids, cloud providers are desperate to save energy anywhere they can. This has made energy-efficient, ARM-based CPUs incredibly attractive for data center orchestration. Experts assert that ARM-based server processors are on track to capture a major share of the global data center market, already capturing roughly half of the new CPU compute shipped to the world's leading hyperscale facilities. Ultimately, the implications for data scientists and AI specialists is that hardware ecosystems always evolve toward balance. The flashy headline-grabbing acceleration of the GPU was the spark that ignited the generative AI revolution, but it is the structured, intelligent orchestration of the CPU that is turning that spark into a sustainable, global utility. As AI transitions out of the research lab and into the real world as a fabric of autonomous, always-on software agents, the central processing unit is proving that it remains the foundational brain of modern computing. The race is no longer just about who can build the fastest accelerator. It is about who can design the most efficient, intelligent, and coordinated system. Does this architectural rebalancing offer legacy CPU giants like Intel and AMD a golden opportunity to reclaim their undisputed dominance, or will agile newcomers reshape the landscape entirely? You are welcome to share your perspective on where you think the silicon race is heading in the comments below. Thank you for watching. Goodbye.